Alrighty, so last time we talked, we were looking at aquifers. And we had two different kinds of aquifers. We talked about confined and unconfined. Using this diagram of an unconfined aquifer, we talked about perched water tables, which were false water tables. Then we mentioned the springs. I reminded you what the rock layer symbols look like, the dots and the dashes, and whatnot. And again, just want to go back to the definitions, so to speak, of the aquifers. The unconfined is easily refilled or recharged. And part of that reason, well, the main reason, is that when it precipitates up here or the snow melts up here, that water can just trickle straight down and keep that water table nice and high. All right? As opposed to, again, don't look at the top word right now. We want to look at the bottom word, confined aquifer. I really need to flip these primary words around after all this time here. A confined aquifer, you see that we have this shale layer all the way across the top, all the way across the bottom. We have a small area up here where it is just that sandstone, okay? And so it's confined because it has that capstone or that lid on it. Now, we'll talk about that a little more in a minute, but for the moment, since we just got done talking about refilling it or recharging it, you see here you have a much smaller area available for recharging, okay? And it's not that that's the end of the world or anything like that, but they are harder to recharge. So you got to keep an eye on how many new systems you tap in, et cetera, et cetera, et cetera. Because you have that very narrow area of recharge. Anything that falls on that shale is just going to go down slope, all right? And you know what? Maybe there's another patch further down where it can expose and recharge there as well. We don't know. All we have is this picture on the screen. Now, what's nice about this, all right, if you look back here, you might not have even noticed. I certainly didn't point it out. When we have a well in the unconfined aquifer, you need to pump it out, all right? You could see the little bucket maybe here that Jack and Jill would have to crank down into the well to get their water, or you've got some electric sort of pump up on top that is pumping out your water. It's just like a straw, okay? You have to suck on it somehow. Here, on the other hand, it is under pressure, okay? And that's what this artesian well is. It's a pressurized well. And it has pressure because you have an elevation difference, or what they call head. All right? So we see the top of the aquifer up there, right where the area recharge is. You're downhill. You poke a hole in it. It's just like that scene out of any old West movie when they're usually drilling for oil, not water. But they poke a hole in the ground and it shoots up all over the place and gets everybody covered in it. That is the same idea here. Okay? This little red line is there to show you that, in theory, be it only for a moment, all right, that water will actually rise to the level of the top of the head. The head attempts to equalize itself, okay? And, again, all of that is because of that containing layer up top, that lid that I keep referring to. So, this is a neat bit of physics, actually, here, and something you can experiment with at home with some very simple ingredients. You need a length of plastic tubing, all right, and a funnel. And you want to attach the plastic tubing to the funnel. And then you're going to need a friend for this one. You need an assistant. You could actually win some bets on this science experiment too here. So you're going to need an assistant. And so you hold the funnel and you put your thumb over one end of the tube and you've got your other hand on the funnel, right? So you have your assistant pour some water or something into the funnel. and you've got to slowly let some air into the system. So you move your thumb up and down a few times and fill that whole sucker up. All right? Then you raise your hand up, do a Statue of Liberty kind of thing. What's going to happen when you take your thumb off? Well, you kids don't do this anymore? All right. So what happens, you take your thumb off, all of that drains out. It's because you have head or elevation difference here. Okay?
Oh, so it's like the Diet Coke and Mentos challenge that people were doing?
No, not at all. That's a pressurized container. No, that's because of whatever they use on the Mentos. It just reacts with the fizzy water. This doesn't need to be carbonated. This is simply gravity. Okay? But here's where you win $5. So you do that once and everything goes everywhere. So then you bet somebody that you can take your thumb off of the end of the tube and nothing will come out. How do you think you make that happen? Any thoughts? None at all. What do we say causes the flow? Just said it like 6 times. Pressure caused by elevation. So what do you do to not have the water flow out? Your thumb keeps it under pressure, yeah. But if you want to take your thumb off, you want to win $5 here. You want to take your thumb off and not have water come out. So what do? You get rid of the elevation difference. You bring your funnel down to your thumb. Okay. So do they seriously not do beer bongs anymore? I literally just described a beer bong to you guys. No? Wow. You heard beer. What? Huh?
Did you say a beer bong?
I did say beer bong.
Don't bring back bad memories from Plattsburgh.
I literally just described one, but in a physics experiment for artesian wells. But that's good that you guys don't do that. You don't need to drink beer really quickly. So at any rate, who knew it was a grand physics experiment? Same thing with lava lamps. There are also a whole lot of physics going on there, and just as much fun, if not a lot safer. All right. So again, the pressure comes because of the elevation difference. Okay. Okay. What's the dashed rock called? Told you guys a bunch of times. Shale. How about the polka dotted rock? The dots. Beautiful. All right. Sedimentary rocks make good aquifers. Shale is a sedimentary rock, but it's a really greedy sedimentary rock. We like to see our aquifers in sandstone and limestone. So artesian well was self-flowing. We told you why a couple times. This pump well goes back to the unconfined aquifer. Okay, we told you you'd have to have some sort of mechanism on the end to suck the water out. And what this is actually about is the second picture there, a little bit of drawdown cone. Okay, and it's about permeability. It's about recharge. And this, again, is something you're very, very familiar with. In fact, some of you may go later today and buy yourselves a slushie. Okay? And so you've got that slushie, and it's fresh out of the machine, and you suck, and not enough to get brain freeze, but just, you're really thirsty, it's really hot, and you want that slushie. So you get to that point, and you're sucking around your straw, and nothing's coming out. Like, what the heck happened here? Where's my slushie? And you could tell just by, feeling it that there's obviously still stuff in there, but nothing's coming in. You take it off and you look in, and sure enough, you cleared out all around your straw, right? And you shake it a little bit, it goes back into. That's all this is showing you, okay? It's recharge, it's refilling, it's percolation, and what's going to happen, we talked the other day about if they decide to build a trailer park or a water bottle facility or whatever, somewhere you've been living a long time, and all of a sudden there's a lot more usage on your water. You might end up sucking air every so often, and if you have wells, you might be familiar with this. All right. when I just got out of grad school, we were in an old farmhouse that was split into 3 apartments, I think. And then further out on the land, there was, out past the barn, there were a couple older folks in trailers. And everything was fine. We were all drawn off, what did I say, 5 households drawn off of 1 well, which isn't the best idea in the first place, but it worked. And everything was fine until like holidays. You got guests over, you're doing more laundry, you're doing more dishes, toilets flushing more. And that was really the only time we'd see it. You turn on the sink and it might sputter and spit at you a little bit. All right? So it's called cone of depression, and there are certainly some ways to calculate it and all that jazz that you don't need to worry about. But I am just letting you know that it is a thing. That it is a thing. All right, so just to recap, you are going to see a handful of questions about this. This is why we're spending so much time on it. And I actually queried you for answers and whatnot. So you have 2 types of wells. You've got the self-flowing and you've got the needs help flowing. All right. The self-flowing is so because it's pressurized. It's pressurized because it has that capstone on it, that confining layer. In our example, we used shale. The pump well is just open to the world, all right, for good and for bad. It's a lot easier to pollute it, but it's a lot easier to recharge it as well. And that's an unconfined aquifer because there's no capstone. Yeah. It is, they use the word fissile. It does shatter quite nicely. However, when it's sandwiched in there between a whole bunch of other rock, I was telling him the other day, it may as well be Tupperware. It's practically an impermeable membrane. Yeah. So but it does, when it gets exposed at the surface, it does break really easily. Pop it out. Yeah. No, and this was drawn for classroom purposes, but ideally, there'd be some more rock and certainly sediment on top of that would keep it down there. But, yeah, no, great idea. But no, when it's sandwiched in place, you know, and that's why they use, it's basically, the shale is clay, and they'll use clay a lot of times to line landfills and whatnot, and underneath the hell they call the ones that you have at your house? Septic systems and stuff. You got a nice clay barrier. Or if you've had to waterproof your basement, you also could put a layer of clay out there. Great stuff. Great stuff. So, anything else while we're paused? Okay, we talked about streams briefly the other day as well. And we mentioned that a spring is different because of its source. Okay?
Is it still paused?
Huh?
Is it still paused the recording?
Oh gosh, I hope not. I'll sort that out later. Sometimes the numbers go away. So with springs, the source of the water is groundwater, the aquifer itself. It's the aquifer leaking out at the surface. And this is just showing you, in probably way too many diagrams, a number of ways that can certainly happen. Now you've got me paranoid about the timer. No, because it says. And the other thing I want to point out, I think we're going to get some slides on it all its own, is this here. You've got a lot of this around this area. The bricks are limestone, okay? And water and limestone leads to caves. So what happens is that the springs work through existing cracks in the limestone, and over time, as the water sits there, it dissolves it out. And then when it dissolves it out, of course, that much more water can go into the space, and then there's that much more dissolving, and it just kind of compounds itself. And so you end up with things like Howe's Caverns and a handful of others that are around here. So that's water and limestone, and like I said, you will see some slides about that at some point. We haven't talked about streams in here yet. We will. There are, above and beyond everything you're going to learn, there are two things that we talk about with groundwater, and that is a gaining stream or a losing stream. And what it's all about is whether or not that stream is in contact with the water table, whether it's in contact with the groundwater. All right, so in this first picture here, we see the saturated zone. That dark blue line at the top is the water table. We told you that's the top of the saturated zone. And essentially the stream is because of that. Now normally you've got, again, precipitation, snow melt, whatnot, that keeps the stream running. All right. In this case, the stream is being fed by the groundwater as well. It's being fed from below by the groundwater. So you've got three sources of input there. A losing stream, on the other hand, is one that is above the water table. All right? And so you still have rain, you still have precipitation, but the water, because of gravity, etc., is going to trickle out of the bottom. So it is much more likely to run dry because it's losing water to the water table. That's the losing stream part of it. Okay. So a gaining stream is fed by the water table. A losing stream is losing water to the water table, or not to the water table, but to the aquifer, just groundwater. Subsidence. Subsidence is simply put, when the ground sinks. All right? And not like a little hole, we've got a word for that one, or even a big hole, but the entire area. Think about your neighborhood, think about your town. Okay, this could be big stuff. And what we have to see is large-scale removal of the groundwater. And it allows all that pore space over time to compact. Think about it. I know I was always bummed out when I was a kid. I'd go to the grocery store, I'd get this great big box of cereal, I'd get it home, I'd open it up, and the dang thing was only half full. All right? And, part of that was marketing. Of course, nice big box to see the cartoon character on, so on and so forth. But the other thing is when that bag that the cereal's in was in the hopper, okay, those flakes or whatever fall down in there, it fills up a lot higher than, what it is when you see it. It's because of all the shaking and bouncing and whatever, the packaging along the way, that those flakes settle in and compact, right? So, so that's what's going on there. Well, the same thing happens with the soil outside. Where we really see a problem with it is in areas of agriculture. All right? I love this photo for a lot of reasons. I don't entirely remember my great-grandfather, but what I do remember of him was that he always wore a white short-sleeved shirt with something in his pocket and a silly little hat, and he was a tiny little Italian man. And that's what this guy reminds me so much of him. So that's one reason I like it. The second reason is oh my gosh, where he's standing is 1977. Up the top of that, their telephone pole says 1925. He quite likely was there since 1925, and probably, again, why we're seeing him in this picture. It's the San Joaquin Valley, some sort of agriculture, right? And California got a lot of water. It depends, right? Sometimes they got too much water, but generally speaking, not really. In fact, they're bringing water down from Colorado River and a handful of other places to help because they have amazing growing seasons. They got decent soil, but they just don't have enough water to feed everything.
Kind of like the opposite of what we have here. Great water, just not a good enough growing season.
Not a great growing season, exactly. So what happened, what we're left to presume, because the textbook I took this out of didn't really explain the photo that well, is that in 1925 the land surface used to be up there, elevation-wise. And then after 30 years, it subsided to that point, and now, 20 years later, it subsided to where he is standing. That's a whole lot of sinking. But they have cranked. Think about all the produce. And now it's a different world, right? We get stuff from Argentina and Chile and Lord knows where you see. You want to look at the labels on your produce and vegetables. It's amazing. It's a world market. But back then, shipping, keeping stuff fresh and everything. Florida, Texas, California. Lots of land. Warm weather all year round. So they were pumping out a lot of vegetables, and think about a grape. Okay, a grape is 99% water practically. So they lost a lot of water. So subsidence. That's a bad thing. Should make that clear. All right, I told you we'd talk about water and limestone. Here we are. The phenomena is called karst. Okay, karst. And it's kind of hard to see in the top picture because it's all full of water there, but that's the idea. You've got the water soaked up into the limestone there, nice and high. It fills in those nooks and crannies and starts dissolving them like we mentioned. And that's all fine and dandy. Even if it looked like this bottom picture and it was full of water, that's fine because the water's in there. It's supporting it, for lack of a better word. It's when it drains that, A, it gets very cool. We like to explore it. But then it also becomes kind of dangerous because it could collapse. So everything that you guys know about karst is the stalactites and the stalagmites, right? Everybody loves those big pointy dripstone things. Does anyone have a way of remembering which one is on top and which one's on the bottom? Stalagmite, stalactite. I never did until I started teaching. Huh? Because why? Because they did. My teacher said tight to you because you'd have to hang tight to the ceiling. So which one of these has a tight in it? Stalagmite, stalactite. All right, that might work. Anybody got another one? Mm-hmm. Yes, that's the way I remember it now. And stalag is G ground. So the other one was that they'd always say mites, and bugs crawl on the floor. So there's mites on. I'm like, but bugs are on the ceiling too. So the mite thing never worked for me. But there's a lot of different things that elementary school teachers say about those. For me, finally, it was the C ceiling and G ground that helped me keep them straight. They're dripstone. So what that means is kind of like the same way you see iron deposits in your toilets or your sinks, or you get, if you have hard water, you get that buildup in your pipes. Over time, just from the water flowing, the stuff that's dissolved in it gets left behind. Limestone is made out of calcite. As we implied several times already, calcite dissolves really, really easy. So, as the water drips, it leaves these little icicle-y things hanging down, very similar to the way icicles form. But it builds up from below as well. Okay? And then there is a third thing called a column, and I'm sure you can guess that happens when the stalactite and the stalagmite eventually join. And this could take thousands and thousands of years. I forget what they said on the tour at House. It's been a long time since I was there. But those have been said. That's why they don't want you to touch them, too. They're real brittle. Some of the stuff is. Those straws are extra brittle. But some of the bigger flowstone things that look like these giant wedding cakes, that stuff is, well, solid as a rock. But their little straws are super fragile. And again, could have taken thousands of years to form. They can only start forming, though, once the water level has gone down. So, kind of neat thing there. And again, these go on to form caves. Well, here we got some pictures: stalactites, stalagmites. So these can also form caves. And that's the stuff that we see in the movies a lot of times. The Great Lakes are all limestone. And back in the day, they used the rum runners used those when you would get shipments coming across from Canada back in the Prohibition. They used them. And also, you know, depending on your coastline, the southeast coast is definitely all limestone. You know, those old stories about the pirates and their caves and whatnot. Because, you know, you think about this stuff, if it's at sea level, right, and you've got your tides, you've got limestone right at the surface, so these things could flood in and flood out. There are definitely many caves out there that are only accessible during, let's say, low tide, okay? And so what a perfect place to hide all your goodies. And here's the evil side of cars, sinkholes. Takes a minute to get scale on this picture, and I honestly don't know why I didn't enlarge it even more. Maybe it's an old, very old picture that gets grainy. Off to the right, you've got a highway. All right. Maybe 2 lanes going this way, 2 lanes going the other way. I don't think there's a turning lane in the middle. But so you have at least a 4-lane road over there. This building went all the way across. This may have been a shopping mall, may have been a factory. This is large, large scale. And again, what happens is that the water eats away at the rock underneath, and it's not usually a problem until it drains down and there's no more supporting there. And you got to wonder, you know, it didn't just happen probably, the draining. It probably sat there for years upon years. And what happened, you know, that one day to set it off, they'll never know. You don't often get a whole lot of warning with these things. Sometimes you start to see some subsidence a little bit, but more often than not, they just go. You know, there's not a whole heck of a lot you can do about it. Now, you hear about these in cities sometimes, and those aren't real sinkholes. What happens is, you'll happen to listen to the news, say a sinkhole opened up in downtown Utica today, and a UPS truck or a dump truck fell into it. The driver was uninjured, something along those lines. All right. It is a sinkhole in that the ground gave way and collapsed, but the reason that happened has nothing to do with water and limestone. As you'll learn in streams, all right, flowing water carries sediments. And what happens is, under many, many cities, you've got very, very old pipes. Be they water pipes, be they sewer pipes, both. And day after day, minute after minute, hour after hour, year after year, a tiny little leak can clear out a really big spot. And as I said, it could just take that one last grain moving away one day, and some poor schlep pulls up with his truck full of all kinds of Amazon stuff that's nice and heavy that day, and goes in to grab a sandwich, comes back out, and his truck's in a giant hole. Again, something we have little to no warning of usually. The blacktop, you know, looks normal until it isn't. So, sinkholes. Let me make that picture bigger while I'm thinking about it. Distorted it a little bit, but there we go. All right. I think this is the last slide. And it is. All right, so that concludes our discussion of groundwater.